In this lecture, we're going to talk about friend functions and operator overloading, which are a couple of the features that we can make use of in C++. In the concept of friends, this is something we want to be very careful in using in C++ because it can get us into a lot of trouble. What basically we're doing is that we are extending rights to the private area of a class to functions or even classes that are not that class, obviously, or not part of that class or part of that object. In most cases, aren't even part of the family, if you will, inherited from that class. So we're giving special privilege, if you will, a key to the kingdom to functions or classes that would not normally have that particular access. So we want to be very careful with this particular tool. There are some legitimate uses for it, and in particular we'll talk about those uses in the context of operator overloading, especially when we're overloading things like the insertion and the extraction operators for I/O and certain other kinds of overloaded functions. And this is just saying what I just said, that you're giving access to the private area and you're violating some of the encapsulation concepts. So we don't control the scope of the friend functions, so usually they're at the beginning of like a header file, and things like public and private don't apply to them. There are some other rules though, and these list what those are in sort of mathematical terms. So friendship is not inherited. If we have a function or a class that we've allocated as a friend to a particular class, when that class becomes the base class or the parent class for something else, that friendship is not inherited, just as you don't inherit the friends of your parents if your parents pass away. It's also not transitive or reciprocal. So just because I make one class a friend of mine and say another class has another class that's its friend, I'm not a friend of a friend. In other words, I can't pass through and get access to something that I'm not legitimately declared directly as a friend of. It's also not reciprocal. Just because I make a class a friend does not mean that I'm a friend of that class and I have access to its private area. And the same with a function. So as the indication here, if a class A declares class B as a friend and class B declares class C as a friend, class C and class A don't necessarily share any kind of friendship relationship in either direction. And if class A declares class B as a friend, class A is not automatically a friend of class B. So class A can't necessarily see the private area of class B, even though B can see the private area of class A. So it's not a bidirectional or two-way street, and we can't pass through because of the friendship with one class into another class because of a different friend relationship. So let's look at an example. Here's an example of creating just a friend function. So you see here that the class SumClass has declared a function setX as a friend, and setX would be defined somewhere else. In fact, it's declared just below. So inside the class definition, we simply have to provide a prototype of the function as well as the keyword friend, indicating that it has access to our private area. In this case, the only thing that's indicated in SumClass is an integer variable SumNumber. A function setX then is defined somewhere else in the program, typically in the same file, but it could be defined somewhere else. That simply takes a reference to some class, because remember, it's not a member of the class, it just can see the private area. So, and then a value, and then it's able to set some number for a particular object of type SumClass to that value. So it has access to the private area of all objects of type SumClass. But we have to tell it which object we're referring to. In other words, I can't just refer to the class generically. So inside main then, I could call setX. Notice setX is not a member of any class and therefore doesn't have an object in front of it like c.setX. And I simply pass it a reference to the object of type SumClass, which in this case was declared as my class, and changing the value to a 5. Okay. Now this example does not illustrate the proper usage of friends. Here I could provide a setX in SumClass that was a member function, and I could say my class dot set x and accomplish the same thing here. So the friend function in this case is not justified, but this does illustrate the syntax of how to accomplish the friend operation very simply. We'll discuss more here in just a moment, the proper as well as improper usage of the friend capability. So we're going to kind of switch gears, but not really, because we'll need the friend function in some cases, to the concept of operator overloading. Operator overloading is a capability in C++ that gives us tools with which we can make our user-defined classes, those that we create, those that we envision and imagine, some of the same capabilities as the built-in classes. You've seen this used in the string class. For example, you can create a string, and you can create a string, and you can use operators like plus and equal and other operators that we use with built-in types like integer and float and double to do things with strings that make sense, but they're not the typical operation that we would see with a number, for example. So we can overload these functions, or these operators in this case, to have special meaning for our particular built-in classes. So we can overload the assignment operators, the plus, minus, etc., the mathematical type operators or binary operators. And we can also overload greater than, less than, etc., etc. In fact, we can overload any of the operators that are relevant to the particular class that we're creating. So it's built into the language. You've used it already. You're actually calling different functions even when you use the built-in types. We're just going to extend that to the types that we create. So if we defined a class, let's say we had a class called simple example. In this case, we create two instances of simple example, SE1 and SE2, and they have some values in them. And we say SE plus equal SE2, SE1 plus equal SE2. So we know in an integer world that would take the value of SE1, add the value of SE2 to it, and store it back into SE1. That may have a different functionality, or certainly a more complicated operational procedure if, depending on what the class simple example is defined as. But it would allow us to create a meaning for that plus equal operator. Okay. So whatever we define that plus equal operator to do, it will do it. One operator is already overloaded for you, and that's the assignment operator equal. And that will work as long as the entity that we're using the equal with, the class, does not have any dynamically allocated data inside it. If it does, then we have to create a separate, what we call a deep copy operator overload, so that those values don't point to the same memory location. Okay, so if we define a function with the keyword operator, this is how we define the operator overloads for any of these. There can be white space or not, but usually they're written together. So for example, here if we had a class that we're going to create called point, we might create a point operator overload. So in this case, the operator overload plus for the addition operator, it's going to take a point P. Now remember that in most cases, we'll see some exceptions in a minute, but in most cases, these operator overloads are operated on two entities of the same type. So in this case, 2 point entities. I only have to pass one of them as an argument because the other one, I'm already inside that object, if you will. I'm calling the plus operator, and when I look at a x equal y plus z, for example, the first value x is already a point, so it's looking for the operator plus function inside of that object. And so I only need to tell it what the second object is. And this is going to return something of type point, so it can pass that across the equal sign, if you will. So in our H file, we would declare that prototype. And then inside the .c file, or .cpp file, as we see in the next bullet item here, we would declare what the function does. And what it does is it returns a point That's computed by taking the x value of the first operand, the one on the left-hand side of the plus sign, and adding it to the one on the second on the right-hand side, which is the p that was passed in, and doing the same thing with the y. In other words, just adding the x values and adding the y values, just like we would add a point. So then in main, we'd create 2-point objects a and b and say c equal a plus b, where c is also a point object, and it would use this particular plus function to accomplish that addition. So we can overload most operators. There are a few that we can't. We can't overload the dot operator, the dot star operator, the unary scope operator, the colon, and we can't do the question mark colon, the ternary operator, as well as the size of operator. Okay, so you can't do those. You can't change the precedence of operators, change the way they work in the precedence table. And you can't create your own operators like a star, which would make sense maybe for an exponentiation, but we're not allowed to do that in C++. You also have to do each operator separately. So simply by overloading plus does not overload automatically the plus equal, because that's technically a separate operator. It's a combination of two, even though they'll do pretty much the same thing. The code will look almost identical. Also note that if you're going to overload, say, plus, then you have to overload both the pre-increment and the post-increment. You have to create two separate functions, even though, again, they'll do pretty much the same thing. Same thing with minus, whether it's pre or post-decrement. Those require separate operator overloads, because technically they are separate operators that have slightly different behavior. Okay. So we want to overload when it can increase the clarity and ease with which your classes can be used. For example, being able to add two things like we do with strings, which results in a concatenation. We don't want to overload them to do things that are counterintuitive. In other words, the operation that you're defining for your particular class should be something that makes sense in a general sense, maybe not just to you, but to others as well. So for example, if we had rational or complex numbers, we could store the numerator and denominator of a rational number separately and then overload plus so that we could add two fractions together, or divide two fractions, or do whatever we wanted to do mathematically with fractions, for example. Same thing with imaginary numbers or complex numbers that have a real and imaginary part. So those would be examples where some of those operations might make sense. Don't do it just because it's cool and it's neat and you want to create something that is obtuse and maybe not obvious to most people. Okay, so we want to make the program clearer, not make it more complicated. Okay, so it's something that's a convenience to the user. If you abuse it, then it can make your program really confusing. People don't understand what it's doing because you're using all these operators that aren't being used in a rational or intuitive way. So you don't want to, for example, make the plus symbol do something totally unrelated to addition or concatenation like we use it with a string. So those would be things we would want to avoid. And there's some other examples here. We don't want to overload the new operator in general, even though we can. In most cases, that can create a lot of problems. So we might create a member function with a different name, or like capital new, but we don't want to overload the new operator itself in general. That's usually a really bad idea. Remember, we can also have different argument lists. So one thing we can sometimes do with operator overloading is to create different versions that do slightly different things. For example, here we're talking about function overloading, which is related to all this. Here we have, for example, 3 different swap functions, one for ints, one for floats, and one for chars. And of course, we could use them intuitively and automatically. The compiler would know which one to use based on the type of the arguments. But in general, that may seem to be a lot of extra work, because if we look at this, all the code is identically the same. The only difference between these 3 swap functions is the data types that are in the argument list. So perhaps there's another way to do that, and we've already kind of gotten a preview of this using the standard template library that we've discussed. But we can create our own function templates as well, in addition to using those that are declared in the standard template library. So we could basically write one function that would do all the work and yet be able to accommodate the different types. So we can create a function template that we can call, and then the compiler will automatically incorporate the right type. So let's look at this. Here's what one of those templates looks like. We use the keyword template, and then in brackets we put what the sort of meta arguments are for the template, as well as the function arguments later. So this says we're expecting you, when you use this template, to specify a type named t, or t is just a dummy variable, just like any other variable. It'll be filled in as needed by the compiler. And then the swap function expects pointers, both of type t. And then inside the code, we have to declare the temp variable of type t, and then the rest of the code is the same as the swap functions that we wrote before, just moving the data around using the pointers. So remember, this is a function template, not a function, so we'd have to essentially instantiate it, if you will. And so we would see here in using it, when we use it and we declare swap as a template function in our header file, then the compiler will put in the proper type when we use it based on the types that are being passed. So in the first example here in this main, the first one would use int for t, second would use float for t, and the third would use char for t. So we basically wrote the function one time, provided a placeholder for the type, and the compiler inserts that. One thing I want to mention as we're going through here is you might know if you pull up these lecture slides, there is more detail and additional examples in the notes part of the PowerPoint. So be sure and take a look at that as you're going through these lecture notes. So that ends this particular lecture, and we'll look at some examples in further lectures.